What's up, AP Stats? Mr. Zamudio here. We're going to finish up these page 5 and 6 on the chapter 14 notes. So we're dealing with the multiplication rule here, but let's do a little recap of what it is. So if you remember, the multiplication rule is when we have two independent events, and we can say that the probability of both of them happening, both A and B, remember that's the intersection, we can just take the probability of A and multiply it by the probability of B. And this is assuming, of course, that they are independent events. What we're going to be dealing with today is a different type of multiplication rule, and this is when they are not independent, but it almost looks the same. It's the probability that both A and B happen. Let's say it's the probability of A, and we multiply it by the probability of B given that A already happened. Now for this, I actually do not recommend using the formula too much. It makes more sense to just take it case by case basis and to really understand what the probabilities are in each problem. Alright, so we'll see how this looks with one of these examples down here. But before we get to that, we got to think about this phrase that comes up a lot with probabilities: drawing without replacement. Right? So let's think of like my favorite snack. We got little cookies. 1, 2, 3, 4, 5, 6, 7. Let's make it 8. All right, so I got 8 cookies in my jar. And let's say I were to randomly select one. The probability that I randomly pick, I don't know, let's say this gray one, is 1 out of 8, right? But let's say I don't pick that one. I pick a different one, and I eat that different one. So now the next day, when I go back to my jar, since I already ate one, there's only 7 left, and this gray one is still down there. Now, if I ask you, hey, what's the probability that I eat that one? Well, that's just 1 out of 7. On the previous day, it was 1 out of 8, but now it's 1 out of 7. And the reason is because we did not replace, that's without replacement, we did not replace the original one that we grabbed and ate. So now let's say I grabbed another cookie. And let's say it still wasn't that gray one. So now I only have 6 left over. So you can see now the probability is only 1 out of 6. So drawing without replacement means there's a fixed number of things we are drawing from. Think of this as like you don't put the cookie back in. So drawing without replacement, this is a dependent probability. Drawing without replacement is dependent. All right. Each of the probabilities is going to change depending on what happened right before it. And over here, this is drawing with replacement. What this would have looked like is if on my first day I picked a cookie, let's say it wasn't the gray one, but then instead of eating it, I just put it back in. So my probability is 1 out of 8 there. But on the next day, since I put it back in, I replaced it, my probability of picking the gray one, there would still be 8 cookies in here, so it would still be 1/8. So it really depends situationally whether or not you have an independent event or a dependent event. So you'll see that in this example here. So in this example, we're dealt a hand of 3 cards, one at a time. Find the probability of each of the following. With AP stats, you'll see a lot of situations where we have problems with probability that deal with a deck of cards. Every year I feel like I have to teach like a little mini lesson on what a deck of cards looks like. So let's go ahead and start with the 4 different types of suits. 4 different suits. All right, we have red hearts. We have red diamonds. We have clubs, which are these like clover looking things. And then we have spades. So these are hearts, diamonds, we have clubs, spades. And we actually have 13 of each of these. We have 13 hearts, we have 13 diamonds, and so on. For a total of 52 cards. In a regular deck of cards, there are 52 total. Now you're probably saying like, okay, so we got 13 hearts, but like, what do they look like? Well, we would have a 2 of hearts, we would have a 3 of hearts, a 4 of hearts, all the way to 10, and then hopefully you guys can recognize that after 10, we get into these different cards. We have a jack, we have a queen, we have a king, and we have an ace. So if I asked you how many 2s are there in a deck of cards, well, there's 4, right? There's a 2 of hearts, there's a 2 of diamonds, there's a 2 of clubs, there's a 2 of spades. How many 10s are there? There's also 4. There's a 10 of spades, a 10 of clubs, a 10 of diamonds, a 10 of hearts. If I ask you how many cards are red in the deck, 26, 13, 13. All right, so now let's see if that helps us with this problem. Here we have a situation where you are being dealt 3 cards, one at a time. Find the probability of each of the following. The first card, the first heart you get is the 3rd card dealt. So the first heart, so we want this to be a heart, and then the other 2 to be not hearts. But now this is where you have to think, when we're drawing cards, when you get your first card, now you keep that card. We are not replacing it. So my first probability, we got to pick a card that's not a heart. Well, looking over here, there's 39 cards that are not hearts out of a total 52. So now let's say you get that card. That's your card. You keep it. Now, how many cards are left in the deck? Since you already took that one, now there's only 51. And of those 51, how many do we have that are not hearts? You just took one, right? We wanted this first one to be a not heart. So right now, you actually have one not heart. So now there's only 38 left. And now you have a second not heart. Now if I look at my deck of cards, there aren't 51. You just took 2 cards. Now we only have 50. And we want this last one to be a heart. How many hearts do we still have in the deck of cards. We haven't touched any hearts. So we still have 13 hearts there. Alright, so that's the hard part there, is recognizing that with these drawing without replacement problems, your probabilities change each time. And then this is just straight up multiplication. You get 0.145 or 14.5%. Alright, if you feel like you can try some of these on your own, go ahead and pause the video or fast forward the video and try these on your own, and then check your answers. So your cards are all red. So we want this to be red, this to be red, this to be red. Well, looking at my layout, I know half of them are red, so 26 out of 52. Okay, but now I picked a card, so now there's only 51. And I also picked up a red card, so now there aren't 26 red cards left, now there's only 25. And then you repeat that for the last one, because now you have 2 red cards. And then using your calculator, get about 11.76% chance that they are all red. So again, this is the probability that we had a red card. This is the probability that the second one is a red card, given that the first one was red. This is the probability that the third card is red, given that the first 2 were red. Alright, we get no spades. No spades, no spades, no spades. Well, we got 13 spades, and we have 39 cards that are not spades. So we have 39 out of a possible 52. So now I pick one. Now there's only 38 out of 50. Nope, not 52, 51. Then we pick another one. So you can see how the probabilities change from selection to selection. Get about 41.35%. Alright, now this one might be a little more difficult. You have at least one ace. So we're still drawing 3 cards, but we have at least one ace. Remember, whenever we have these at least problems, I want you to think of the complements. You could have 0 ace. You could have 1 ace. You could have 2 ace, 3 aces. And we want the probability that we have at least 1, right? So we're looking for this. We want the probability that we get 1 or 2 or 3. But that's difficult. Let's just figure out this probability and subtract it from 1. So we can do 1 minus the probability that we have 0 aces. So 1 minus, our first one has to be not an ace, our second one has to be not an ace, and our third one has to be not an ace. Now remember, an ace is not a type of card. An ace is one of these. And remember, we have 4 aces, right? We have a heart that's an ace, we have a diamond that's an ace, club, and a spade that's an ace. So if there's 4 aces, we have 48 non-aces, right? And what we're looking for here is we want each of these to be non-aces. We want 0 aces. So there are actually 48 out of 52 cards that are not an ace. Now we pick that. Now there's only 51. And 47 cards that are not an ace. 46 left over. Do this probability, and we get 0.217, or about 21.7%. Okay, guys, so that is the drawing without replacement. All right, we can see that that is a dependent relationship. The probability of the second one depends on what happened the first one. The probability of the third one depends on what happened the previous ones. Okay, I would say the tree diagrams we will save for another day. What I would like you guys to do is this practice on page 6 towards the bottom there. I am going to give you the answers to these problems, and then you guys can check your work. And here are the answers.